Hello, everybody. So today, Divkesh and myself, Julie, will be presenting on our EE312 control system mini project, which is the magnetic levitation system. Our main objective for this project requires the following. It's to design a magnetic levitation model with a 98% settling time less than 1 second and a zero steady state error for step input. The magnetic levitation is a technique whereby an object is suspended with no support but magnetic field. The main desire of the system is to recommend an appropriate controller for the positioning of the ball in the air with the use of the magnetic force. The principle of magnetic levitation has been known over centuries and is widely used in magnetic bearings, levitation of wind tunnel models, high-speed trains, vibration isolations, and many more. So the magnetic levitation system is mainly a controller design. The controller is vital for the stabilization of the system and is made robust. The controller designs implement theories as follows: the PD controls, root locus and frequency control, state space control, adaptive control, and the combination of the above series. As you can see, it's a block diagram. So basically the input is being supplied to a controller and then to a force actuator where the ball is levitated. This setup is a closed loop system whereby the position sensor and the sensor collaboration is what causes the feedback. So as you can see here, it's the setup of the magnetic levitation system. It's mainly made up of the electromagnet, a ball rest, a ball position sensor, and a steel ball. Moreover, the sensor is the core component that requires high precision and stability. So this is where our results and calculations are mainly based on the sensor and the ball and the other components. Here is the setup with the control. So the system is inherently nonlinear, unstable, and described by highly nonlinear differential equations. Therefore, a PD control was used to make the system more stable. It is well established and is used so that it's driven towards a target position or level. So mainly here it's talking about the position of the steel ball itself. Moving on, I will now give this time to my colleague Divkesh to elaborate further on the methodology and so forth. Go.
Okay, thank you, Julie. So I'll be discussing the methodology for our project. So it is divided into 3 phases. The first phase, we have to make an assumption for the overshoot since it was not given in our specifications, followed by calculation for the damping ratio and natural frequencies, and state the desired pole rather. In phase 2, we'll calculate the transient response and add a compensator 0, determine 0 position on axis, and in final phase, we will calculate the gain and construct a negative feedback system. So this is based on the fact that we are designing a PD controller and a lead compensator. So this methodology is for that. Next. Since our transfer function was already given in our manual, so the next step, as I discussed previously, is to find the damping ratio and the undamped natural frequency, which is Wn. So it was found to be 0.59116 and 6.7664 respectively. And since our damping ratio is between 0 and 1, we can say that the system is underdamped. Next. Okay, so once we have found our damping ratio and our frequencies, we can make the equation for our desired poles, which is -4 plus minus j 5.457. And basically for the calculation part, we have done it in our, we have included it in our report. But if we would have included it in our presentation, it would take a lot of time. So what you can see on the screen right now is the final equation for the controllers. For the phase lead compensator, the equation was the gain rather was found to be 1297.37 plus S plus 31.329 whole thing divided by S plus 128.57. And for the PD controller, the control system was found to be having a gain of 7.98 at S plus 128.57. So for now, I'll be taking you to the simulation part to show you what the codes we have written. Okay, so as I mentioned before, we have designed a lead compensator. So for our project, the gain was found to be 1297.356, which we have declared at the beginning of the coding. Next up is the transfer function. And this is the same transfer function which we obtained from the lab manual. The only key difference is that the denominator has been factorized. So just by looking at the denominator, we can say this system is unstable, because when plotting the root locus, there will be a plot of positive 31 towards the right hand side. So to demonstrate the root locus system data, I have just given a G as a feedback and stored it as SYS1, system 1. So we have our gain, we have our transfer function. The next thing which we had to do is to derive the control block, which is in the order S plus A upon S plus B. So in order to make our things easy, we have just used the numerator as S plus 31.329. This is the same as the denominator of the transfer function. So that basically it cancels out and we only have to calculate for theta in our calculations. So now we have our gain, our transfer function, and our control block values. So one thing to note is that all three of them are connected in cascade. So we can just simply multiply them and declare it to a value G3. And yeah, once done, we can plot this. So I have made two figures. One will be showing the subplot for the step, the original step without any compensator, and with the compensator, followed by subplot in figure 2 for the original locus without the compensator and the root locus after the compensator. So I'll just run this. Yeah, so as promised, for figure 1, this displays the root locus before the compensator. As you can see, the pole is at a negative 31.3 for both of them. And for this root locus, the final the pole which we added was yeah, negative 31.7. This should be the same. Yeah. So this is for figure 2, the root locus. And for figure 1, which was supposed to show the step function, this was the original step function without the compensator towards your left. And we had to get a settling time of less than 1 second. Yeah, I can successfully say that we were able to receive a settling time less than 1 second for the value 1. So this proves that the coding done for the lead compensator was actually correct. So I'll just take you through the other section, which is for PD control. Yeah, PD control. So just like our lead controller, we have used a similar approach by declaring the gain at the beginning, followed by the transfer function and the control group in this case. So just like previously, it is being multiplied since it is connected in cascade and a feedback is given. Again, the step function is displayed in figure 1 and root locus is displayed in figure 2. So I'll just run this code so you can see it. So in figure 2, so these are the points which we also saw previously. It's the same, doesn't change. But now, as you can see, the root locus is intersecting at our desired points. And the value 429 is the new pole which we had, new zero which we had added, that is negative 129. And for our code, yeah, so it is roughly negative 129, but else true. So the moment of truth for our step function, this was our initial plot without the controller, and this was our plot after the controller. And the settling time for this particular plot is at 0. Yeah, it is almost the same as the previous one. There is a slight difference, but it is almost the same. So basically, the PD controller and the LED compensator, these two are quite similar. So basically, we were able to design a PD controller and also a lead compensator, and we were quite successful at it. So yeah. Okay, so we have just seen our simulation part. Now we can just move forward to the conclusion. So to conclude, I can successfully say that the LED compensator and PD controllers were designed and simulated, and all the specifications were met with an assumption of an overshoot of being 10%. So that was all from our side. And all the calculations will be included in our final report, and the M file, the codes will be included in the description below. So, thank you so much for listening.
Thank you very much.